wants to come and show. Okay. Do you see the camera?
Yes.
Okay. Personally, I don't see it, so I was a little surprised, but anyway. You can lead me, move left and right. Wait a second. Okay, no, I don't see myself, but it's good. So in this example, we just see that we have a specific vector xb, which has the projection of 4 and -1, and projection 4 is on this vector 1, 2. So 1, 2 is this vector in red, which is shown here. And then we have 4 units of this vector. So we have 1, 2, 3, 4. And we have also -1, which is this vector here, which is the other basis component, which is -1, 1. So if we carry on this little vector from here, we bring it here with a minus sign, we go to this point, which in the standard basis, it is 5, 7. So here we get 5, 7. And similarly, but this might be a little difficult to write this on the board, because we have -25, so we are talking now about the basis S. And in basis S, using these representative matrices, which are composed by the columns of basis B and columns of basis S, we find out that this is this was 5, 7, this is standard basis, and -25, 16, this is according to basis S. So this is where we see it, and apparently this point is going to be 16 vectors, which are 5, 2, and 5, 2 is this point here. So we have to have 16 points like this, which goes like 1, 2, 3, 4, 5, and 16 units. Then we have to take minus 25 units of this other vector here. Anyway, it's hard for us to draw this one to scale, but it was relatively easier to denote on the board that this point stays fixed, and the only thing that changed is whether we are going to use this as a basis, okay, or whether we are going to use this as a basis. So any point here is by projecting from here and here, and this is what we see in this example. Now, with this example covered, we want to move to another important concept, which is the concept of similarity. Now, the change of basis and similarity, let me find this. So, the change of basis and similarity, we want to say that the essence of what we are going to see in this case is that the similarity is defined whenever we have that the matrix C is equal to a matrix of P inverse times A times B. Okay. So we are going to define in a very short way, for the sake of understanding it, what we mean with this. But at this stage, the change of basis and similarity, this similarity, we are going to consider it only when A is what? What do you understand when we see this?
Square.
Yes. So apparently, only for one matrix A, which represents a linear transformation, is a square one, we can define another matrix C, which is similar to A, and this is possible only when C is equal to P inverse times A times E. Okay, so we're talking only about these matrices, and then the summary of the whole theory on the change of basis and similarities, I can put it shortly as such. So any vector in the standard basis, allow me to write this one SB. This is equal to any basis PB times the projection on the same point according to basis B, right? So this is possible. We understand very well what we mean with this. Now, we want to see what happens to a linear transformation T on a vector x. We know that this is equal to A times x, so we can always define a matrix A which replaces the properties of the linear transformation T. And at this point, we just need to substitute, instead of this x that we see here, let's substitute it with this expression that we have here on top. Okay. So just substitute it here, and we are going to get that this is A times matrix PB times the x, which is according to the projection onto B. Okay. Now, we want to see what happens to this linear transformation T according to a basis B prime. Okay. Then this would be equal to PB prime inverse times the linear transformation itself, Tx. And this would be equal to PB prime inverse times A times PB times whatever is left on xb. Okay, so this is the.
What does B prime represent?
Say it again.
What does B prime represent?
B prime, this represents the case. This is the general case when A is not squared. Okay, B prime and B, it represents two different bases, which is defined as what we said here before. We said that we can have a matrix A, which can be projected differently on as AB2 and differently on AB1 or B and B prime. Now, this is the general case whenever A is not squared, but the moment that A is squared, now we will assume just the transformation from the standard basis to only one basis. Okay, let's use for the moment only this type of transformation, and to do the formal definition, we have a theorem which the statement, the verbal statement of this theorem, we can also simplify and describe this with a simple notation. So the theorem states that for any linear transformation which allows the transformation from Rn to Rn, so it is clear that the A in this case is going to be a square one. So T is a linear transformation. So that's the first given. And also given that B is a basis which is composed of vectors x1, x2, and xn. So this is the basis. Then we say that let the T of x be equal to ax. So the linear transformation on x would be equal to ax. And let P be equal to x1, x2, x3. These x1, x2, x3, these are all vectors. And this vector P, matrix P, is called as this. So you can read it from here. So matrix P, it will be a transition matrix which makes possible transition from one domain to another. That's why we see this as with this representative matrix notation. And then, if this is the case, if we have a linear transformation, if we have a basis that looks like this, matrix A is defined as a matrix representing the linear transformation. Given this basis P, then we can say that this linear transformation of Tx according to basis B is defined as P inverse times A times P, where this vector x is a projection according to basis B. Now, this definition here, so the theorem, is just whatever we see here. The third statement here is considering a case where we are transforming from basis B to B1, but here the difference between this point and this point is that we are considering A n by n. Okay? It will become clear why A can be only a square matrix. But now, in principle, whatever this theorem is stating, we can also represent this in shorter version as such. So A, it represents linear transformation T in standard basis. Let me write it like this. And then the P inverse times A times P represents the linear transformation T in basis B. Okay? So this theorem on top, this is equivalent to this table, which is a little more concise. Now, before we want to continue with an example, but before we go on with this example, I want to ask you one question, which is the following. Let's have a look at so what is this equation? X squared plus y squared equal to 1. What is this?
This is
Circle with
the
center origin.
It's a circle.
Unit circle.
Minus 1, minus 1.
Unit circle.
What about x squared plus 4y squared equal to, let's say, equal to 4? What?
Ellipsis.
Ellipsis.
This ellipse, where does this ellipse intersect with the x and y axis?
X2, epsilon 1.
So let's do it like this. When x is 0, what is y?
1.
1 minus 1. When y is 0, what is this?
2.
This is 2 and minus 2. This is true. So we see an ellipse, okay? Okay, then I'll start with this example, but for this one, I'll need the board. Now, what we're going to see now is that it's just an example which can be used to understand the fundamental or the importance of the basis change. Now, given this is our example, we have here 5x squared minus 6xy plus 5y squared. This is equal to 2. Okay. So here we have one equation. Now, what we want to do at this stage is that we like to write this expression using matrix notation. Okay. And how can we do that? It is very essential. These types of wait a second. Okay, sorry, this is not good enough. We want to write in a notation which is x transpose times A times x. This is equal to 2. This is what we want to do. Okay, this is vector, matrix, vector again, and who can do this? Now, one thing that we can do is that this vector x, we can denote vector x equal to the two variables that we see as important, which is the x, y. If this is the vector x, which is, what is the dimension of vector x? It's 2 by 1. X transpose is going to be x and y, which is 1 by 2, right? So then we write it like this. We say that the vector x, which is xy, size 1 by 2, times the matrix, which is...
definitely be 2 by 2.
Say it again.
It will definitely be 2 by 2. Because if it's not, then calculations cannot be done.
That's true. This is, yeah, this can be, should be 2 by 2, but what we can denote it, we can denote it like this. So this is the matrix 2 by 2, and then the other vector, this is going to be xy, which is 2 by 1, and this is all equal to 2. Now, if you multiply all of these sizes of the matrices and of the vector, do we get a scalar?
Yes. The first two give a 1 by 2 matrix.
Yes.
Then times a 2 by 1 matrix give a 1 by 1 matrix, which is a scalar.
That's correct. Thank you for confirming this. So,
Ato matrica në e morëm rastësisht nga doli ajo.
can you see how we can find this? So let's multiply. Let's see what we get if we multiply these two matrices.
We get a 2 by 1 matrix.
We get the 2 by 1 matrix, but I want you to notice something here.
5x minus 3y minus 3x plus 5y.
This is 5x
5x squared
y minus 3x
Plus 5y.
5y. This, we multiply this one with xy. Okay?
You get the equation above.
Yes, we do. So then we'll get here 5x squared. Actually, I might even remove this one, or let's keep it like this. So this is 1 by 2, this is 2 by 1, and finally we get 5x squared minus 3xy minus 3xy, because we're multiplying now the y with the second element, plus 5y squared. This is all equal to 2. Well, so this is 1 by 1, it's equal to 2. So it's almost clear that this expression, this identity here, it is equivalently reported as in here. I believe, would you agree with this? Okay, so then what we can do here is that we have a representation of x and y, which is the Cartesian coordinate system. So let's assume that we are given initially the standard basis. Then let's try to rotate. Let's do it like this. Let's rotate the Cartesian coordinate system. Let me call this CCS, Cartesian coordinate system, by an angle of pi over 4. Okay. So what is the rotation by pi over 4? It's going to be a matrix where theta is pi over 4, which is equal to cosine pi over 4 minus sine pi over 4, sine pi over 4, and cosine pi over 4. Okay? So this is what we're going to do, and this matrix for this specific angle is going to be equal to 1 over square root of 2 of 1 minus 1, 1, 1. Okay, so this is the rotation matrix, which can rotate the whole Cartesian coordinate system by an angle pi over 4. Then, what we come back to this schema that we have here, and we have we are in the standard basis. Let's assume for a moment that in the standard basis we have x and y.
Can you move the camera a little bit up?
You need it up?
Yes.
Okay, actually, is it good?
Now that's perfect.
I don't see the camera myself, so it's not the best situation. But you can help me with assigning this. Now, so in the standard basis, we have x and y. And what we want to do here, in principle, is that we want to see what this identity provides for us. Okay, what is the graph of this? How can we graph this? And we are giving an attempt to simplify the problem somehow. So this is x and y, and let's assume that we want to represent the same these points, which are described by this graph, by this identity. We want to change all of these points from x, y to capital X, capital Y. And how can we do it? In order to do that, we can say that we know that always the small x and y, so this is x and y, this will be equal to 1 over the square root of 2 times the matrix, which is 1 minus 1, 1, 1, times the capital X and capital Y. Okay, why can we do this? Because we know that always we go to the standard basis by multiplying the matrix times the other basis, the non-standard one. So now, what we need to do at this stage is that we need to write down this polynomial. And this polynomial, we can write it like this. I believe you can see this part of the board, right?
Yes.
So we have here, wait a second. Maybe better we write it here. So this is going to be 5 times the small x squared is equal, or let's do it this actually. So here x is going to be equal to 1 over square root 2 times capital X minus capital Y. Okay? And the little y, this is equal to 1 over square root of 2 capital X.
Oh, we can see down there.
You lost it. Okay. So let me use this part of the board. It looks like little x is 1 over square root of 2. Okay? So this would be the capital. I believe this is correct. And now these two expressions, which we obtain by using the transformation from the standard basis to the new basis, let's write down the 5x squared. The 5x squared, this would be 5 times 1 over 2 times x squared minus 2xy plus y squared minus 6xy minus 6. The little x is 1 over square root 2 x minus y times 1 over square root of 2 capital X plus capital Y, and plus 5 y squared. The 5y squared, this would be 1 over, this is going to be 1 over 2, because square root of 2 squared, we will get here 1 over 2. This is x squared, minus, this is plus xy, plus y squared. I believe this is all. This is equal to 2. Now, if we look at the terms that we see here, is that we have 1x squared is here. Then maybe it's best if we simplify this a little further, because let's do this. So this would be 5 over 2 x squared minus 2xy plus y squared minus, this is 1 over square root of 2, 1 over square root of 2, this is 1 over 2, this makes it a 3 here, and then we get here x squared minus y squared plus 5 over 2 of x squared plus 2xy plus y squared. This is all equal to 2. Then let's have a look. We have here x squared is here, and then we have another x squared. We get 2x squared. We get 5 minus 3. We get a total of 2x squared. So this is 5 over 2, 5 over 2, 5 minus 3, we get 2x squared. Okay, so this is also considered. And then we have this here, we have 5 over 2 minus 2xy plus 5 over 2, 2xy, this is gone. And then we are left only with the y squared terms. So here, this is y squared times 5 over 2 plus y squared times 5 over 2. We get 5y squared plus 3y squared what do we get?
We can multiply it by 2 so that we give you the 5 over 2.
Yeah.
8y squared.
Yes, that's true. We get 8y squared. This is equal to 2. Okay. So when we see this expression, we can
divide by 2.
Say it again.
Divide by 2 both sides.
We can do it. In fact, I want to leave it like this, but we can also simplify this a little further, which will be the following. This is x squared plus 4 y squared. This is equal to 1. Okay. So now we can ask the following question. We had this identity initially, so we started from here. Okay. And then we represented this in this form, such as x transpose as a vector times a times x. This was equal to 2. Now we see that this one and this one, and you correctly said that this is equivalent to this one. That is true. Let's try to write down the same vector here now in the matrix notation. If we try to write this one in matrix notation, we will have the following: x and y, okay, times what? What can we write in this matrix? We get this times so this is what we get, right? One thing that we notice is the following. So this matrix, which does the multiplication of the x and x transpose, is now diagonalized. Okay. So we see that off-diagonal terms are 0. So let me write this one off. So off-diagonal terms, they are equal to 0. So we have done, by doing this rotation of the coordinate system, what we have achieved is that we have diagonalized our representative matrix. Okay? So, which means that this matrix, which here in this domain can be 5 minus 3, so this is 5 minus 3 minus 3, 5. And here we will have the 2, 0, 2, 0, 0, 8. So this is how we can represent this one. Now let me say this. You do not know yet, probably you don't understand fully what we are doing here, but it will become very much more clearer when we do the eigenvalues and eigenvectors. So we have said before that the most important element that linear algebra provides for us is the diagonalization, okay? And it looks like we kind of did it. And the thing is that what is what's the name? What is the graph of such an equation here, or this equation here? X squared plus let's use this one here.
It's an ellipsis.
Can you move the camera a little bit lower?
Lower, okay, so let me write a little. Actually, I don't see my own camera, so if we stay minus delta destra sinistra, let's do this. I believe you can see this one.
Yes.
Yes, okay. So we have here x and y, and the new coordinate system is going to be 1, which is rotated by 45 degrees. So this is our capital X, and this is our capital Y. And in this new coordinate system, similarly to what we did before, if we assume that Y is equal to 0, what is X? X is going to be 1 minus 1, right? But when X is 0, the Y is going to be half and half. So this is going to be 1, 1, and we're going to get this expression. Okay, so here we see an ellipse, but it is much easier for us to distinguish this ellipse if we use the new coordinate system. So now the question is, okay, we just did this rotation, but how? Let me think for a moment. How can we predict that we need to do this? Because we said that we are going to rotate the system by this much. The question is, how can we know this? How can we know that a certain rotation or another operation is the best rotation or the best linear transformation that can diagonalize this matrix A? So, so far, we have seen me drawing sketches like this. This is the standard basis we have set. This is basis B1, basis B2, this is matrix A, and we do the basis change only for this matrix to be diagonalized in a different domain. Okay, so let's not forget this. And this is where we have the solution. And out of the solution, if you allow me, we can erase this part because you can redo those. But this is just proving that this equation at the top is equal to this equation here at the bottom. Okay? And probably, yeah. And then, yes.
Mund ta shpjegosh pak si do lej elipsi aty?
Cila?
Ellipsin. Si do të elipsin aty? Pse do lej elips?
Ellipse, yes. So why do we get here an ellipse? The fact is that we have here, but you remember that a few minutes ago, we plotted the graph of a circle and of an ellipse, right? We did this in a similar way. We said that x and y, these were the orthogonal Cartesian coordinate system. All we did is that this x and y we rotated them by an angle of 45 degrees, which brings this one, so this angle here is 45 degrees. We rotate it like this, and then we want to plot this graph. What is, if we set x is equal to 0, if x is equal to 0, what is y? Y squared, it will be 1 over 4, right? So if y squared is 1 over 4, y will be 0.5, will be 1 over 2. Okay, this is 1 over 2 whenever x is 0. So this is where we find this 1 over 2 minus 1 over 2. Then similarly, we say what happens when y is equal to 0. If y is equal to 0 in this expression, we get x squared is equal to 1, which means that the x in this axis is going to be 1 minus 1. Okay? Is it clear now? So we just join these points, and we know that this type of equation is going to draw an ellipse. Is it clear now?
Yes. Thank you.
Thank you. You're welcome. Now, so I believe now this looks like it's clear. That's good. And one other thing that we can add is the following. So, what is? Can you have a look at the columns of this matrix A? Ne keni thënë që kolonat e matricës që bën linear transformation, kolonat janë bazat, janë vektorët që përcaktojnë bazat e reja. Mund të konfirmojë ti këtë? E mbajmë. So what I'm saying is that the matrix that does the change or the transformation, so we're on this A, but assume that this is P. What are these columns? Çfarë do kolona dhe plus? Janë bazat e reja. So you might have seen
Pozicionet e reja të I hat, J hat.
Yes. So the way that we denote it, let's take this out, is the following. Let me take also this out, because this we know it now, but we need to keep this one still here. So in this basis, apparently, we have 1, 1 minus 1, 1. This is 1, 1 minus 1, 1. And in this standard basis, for standard basis, what are the columns?
1, 0, 0, 1.
Perfect. Thank you for confirming this. This makes me feel that you are following, because this is very important. I want you to follow very carefully. So initially, in the standard basis, when we were talking about the small x, the lower capital X and Y, the basis, it was 1, 1, right? Now, the new basis, it is 1, 1. Where is 1, 1 on the graph? Maybe it's best if we do it like this. So, the standard basis is 1 here, 1 here. It is clearly like this. The new basis, it is 1, 1, which is this vector, okay? And the other one is minus 1, 1. Minus 1, 1 is this. So the new basis, sorry for not drawing it perfectly, but the new basis is this. Do these two red vectors constitute a basis for R squared? Yes, they do, because they are not linearly dependent. So you can either look at the, you can use the basis, the vectors in red, or the pair of vectors which are in black, which are these in fact. So these are clearly here, and this is the new basis. Okay, that's good. Now, I want to do something very, so that I have everything on the board. I will explain the eigenvalues and eigenvectors right away, without spending too much time and without going into the very details, because I want you to see this one on the same board. Now, you'll see what we'll have in the next minutes. I want you to ask one question. We said before that applying any matrix A on a vector x, what does the matrix A do to a vector? The first thing is that it rotates the vector, right? The second thing is that it can change the length. It can length modification. I can say this one. It modifies the length. Right? Would you agree with these? In the last week, we said, or let's say, what is this matrix? This is 1, 1 minus 1, 1 times the vector 0, 1. What is this? Let's see, this is 0, this is minus 1, 1. So what is the magnitude of this vector? The magnitude here is 1. What is the magnitude of this vector? It's square root of 2. So what the matrix A does, it changes the magnitude, it also rotates it. Now, let's consider a special case where the vectors are not rotated. Okay? We don't want to rotate those. We just want to change the magnitude. Okay? How can we do that? Or how can we represent it? The best try is the following. We can have a square matrix, okay, A.
And it must be diagonal with same entries.
Sorry, say it again.
Diagonal matrix, but with same entries. Example, all ones in the diagonal part.
And what solution would this provide?
Because if we want to change the length of a vector, it means that we must multiply it with a constant or a scalar.
Yes.
Or a diagonal matrix with same entries.
You are right, that is correct. Okay? But what you are saying, it's a little bit complex. I hope that your answer...
Or scalar times the identity matrix.
Perfect. So this is how we can denote this. Okay? So we want to use, we assume, we want the matrix A to just change the length. But the question is this, is it even possible? Is it possible that the matrix A does not rotate the vector? So we just gave an example here. We have a matrix A, we multiply it with some vector. This is what we get, right? We can calculate what the angle is. I think the angle, we did this last time, is like 3 pi over 4. Okay? And in the last week, I gave you a homework, which some of you have solved this one and have emailed it to me. The question to you, it was this. Find a vector AB that when you apply this matrix, you get the angle 120 degrees. Okay? As a reminder, the homework, it was like this. Find, let me write this one here. This is 1, 1, minus 1, 1.
Can you lower the camera, please?
Oh, you don't even see this part? I really need to make it. Medvedec se fine.
Скажи, фиш, по камеру,
But I'm not very good at providing discrete values.
Oh.
Okay. So we said that the question was, given this matrix, multiplying with a vector AB, find another vector which is CD, but the angle between A and B is equal to 120 degrees. Okay, this was the question of the last time. Some of you solved it. Now it looks like depending on these vectors, the matrix can rotate them with specific angles. Okay, or it may be even it doesn't even rotate them at all. Maybe it doesn't rotate them at all. So apparently, there are some vectors in the R square for which we can write this expression. Okay? Then the question is, what is this vector? Чашки вектори, що пишемо, зоймете матрици чекам, nuclear dollar vector, сидоиченко. So how to find this? Let's take this term to the other side. We can do the following. We can say matrix A minus lambda I, so we subtract this like this, times the vector x, which is n by 1. This is equal to the 0 vector, which is also n by 1. Okay? So this is one way how we can solve this. Then, how can we proceed next? Have you ever seen this before? What does this mean for you?
Finding the solution of a homogeneous system?
Exactly. Which means also finding the null space
Yes, the null space.
of this matrix. Okay? So here we have a new matrix A minus lambda I, of which we need to find the null space. Okay? What is the first solution that comes to our mind?
X equals 0.
X is equal to 0, which is the trivial
The
solution.
trivial solution.
Now, we don't want the trivial solution. We want a more general solution, okay? So we don't want this. But the question is, and by the way, I think we all remember that the range of a matrix here, and this matrix, let this matrix be equal to A minus lambda I, okay? So this is the matrix B, which we are defining it here, and we are looking for Bx is equal to 0. So we are looking to find for the null space of B, and the null space of B is different, for what values of x is this identity 0? We can say that x is different from 0 if determinant of B is what?
Zero.
Easier.
It's 0. Thank you for confirming this. And let's remind ourselves, why is this the case? This is the case because we know that the x different from 0, it is going to define a linear combination of the columns, okay? And this is going to be different from 0 if determinant is 0. Why is the case? Because if the columns or the rows are linearly dependent, by combining them or by adding them, especially what we have often done is that when we obtain the reduced row echelon form, we used to get a row full of zeros, right? We have done so many examples like these, and we know that if the rows are linearly dependent, we try to
It means that there are infinitely many solutions.
the bottom row is full of zeros, and we know that in any matrix, if we have a row full of zeros or a column full of zeros, determinant is this, okay? So we want the determinant of B to be equal to 0. But it looks like determinant of B, it does not depend on the A directly, but it's a function of lambda, okay? So it looks like there may be some values for lambda, which can make the determinant 0. Now, I want to take away this part. It's gone. This was a reminder for last week's homework. So we are still talking about for matrix A, which does not rotate some of the vectors. Let's take this away. Okay, this may go. And we're trying to solve the problem again. What is A minus lambda I? A minus lambda I, we can write it A minus lambda I is the following. Let the A be this. We have 5 minus lambda minus lambda, right? So this is this matrix, okay? And the determinant of this one is equal to 0. So what is the determinant of this matrix? This is this term times this term minus the product of these two numbers. Would you agree with this?
Yes.
Yes.
5 minus lambda times 5 minus lambda minus 9, this is equal to 0. So what we get here is that we get lambda squared minus 10 lambda plus 25 minus 9, this is 0. Then we get, apparently, we get a polynomial of the second order. Which means, yes.
Ajo nuk del -5 minus lambda katror,
C'était Mr. Pace?
minus lambda katror. Oh, jo, më fal, se pash një më plus një minus.
So we are good, right? Okay. So this is, but for a moment when you talked, I even thought about it, but apparently I was wrong right from the beginning. So this is lambda squared minus 10 lambda plus 16. This is equal to 0. Now,
Lambda minus 2 times lambda minus 8 equal to 0.
what did you say? Lambda is equal to what?
2 and 8.
2 and 8, that's true. But what is essential is that this polynomial, which determines the determinant of the matrix, we call this one characteristic polynomial. Okay? Characteristic polynomial for a 2 by 2 matrix, it's a second order polynomial. And the second order polynomial, we expect to have two solutions, two values of lambda. Now, this polynomial here, we can write this one, lambda minus 2 times lambda minus 8. Okay, and this is equal to 0. So it is almost obvious for us that lambda, so we have two solutions. We have lambda 1 is equal to 2. Okay. Now, if lambda 1 is equal to 2, let's go back to what we were saying. We said that we have a matrix A, right? So this was a given. So let's not forget. Let me write this one. Sorry, give me a second. So given a matrix A, this is the definition of the problem. The question is find lambda and find the x. Yes.
Aren't characteristic polynomials used in the vargjet përdoren duket për të shtuar nga forma rekursive në formë normale?
Mos ju fut atyre se janë gjëra të tjera.
Po e përdorim për herë parë. Ju për herë parë po e përdorim sepse është herë parë.
Jo, them polinomet karakteristik më duket që mund dhe këto të vargjet, domethënë që nëse kthem për shembull Fibonacci ta kthesh në varësi me indeks, varësi të indeksit.
I don't remember whether it was called that way, but characteristic polynomial, you see it often. You see it also in differential equations. But having it, but I think when they do the Fibonacci numbers, if they find a subsequent Fibonacci series of numbers as using a matrix, yes, you can use a characteristic polynomial there, because calculating subsequent numbers like Fibonacci numbers, it takes less time if you use the matrices. But now that you mentioned such a beautiful example, I just want you to remind me, after we are done with this, remind me to talk about the Fibonacci number again, okay? Because yes, you might have seen it that way, but it is very essential for us to discuss why it could be used a matrix when we try to find the series of Fibonacci numbers. So please help me, remind me after we are done with this if I forget it. But leaving aside for a moment the Fibonacci numbers, let's come back to this problem. What was the new problem that we are discussing right now? What we had is essentially, we were given a matrix A, which is shown here in the standard basis. This is how it looks like. And given A, find lambda that is going to satisfy this condition, right? And the other question is, find x. So this is how this type of problem is defined, and this is the new definition of the problem for all of you. Then, apparently, so in principle, we have to find a vector which is not rotated by a matrix, okay? Now the point is that, does this vector even exist? This is another question, but for the moment, we found lambda first, okay? We wish to find x because this is what we care, but we find lambda first. And then it looks like we can have a vector x, which, if we multiply with this matrix 5 minus 3 minus 3, 5, which we observe it here, which we extracted it from here, apparently this matrix can multiply a vector x, which is equal to 2 times the same x. Okay. Then how can we find the x? Let's see. For this lambda, we can write the following equation. We have 5 minus 3, 5 minus 3 minus 3, 5 times the vector. It has two unknown. We have a and b. This is equal to 2 a and b.
Can you move the camera to the right?
Okay, so how much did you lose? I don't want to lose the other edge of the board.
I only see the number 2, then I don't see more anymore.
Okay, then I have to continue for some time.
Просто и не чик the camera.
I'm afraid you're going to lose the other edge of the board, so okay.
Просто надо Taiwan.
No, we'll go back.
Okay, it's perfect.
You need the whole board, otherwise you lose it. Okay, this is what online learning is about. So here we have this system of equations. The unknown is the a. What do we get for the first equation? The first equation, can somebody write this for me or tell me what should I write?
PSA minus 3b
Yes.
by
Is equal to
2a
2a. What is the other equation?
minus 3a plus PSB by 2b. Plus PSB by 2b.
Now, how many unknowns do we have here?
2 paniora 2 equazione.
Okay, we have two unknowns, a and b. How many equations do we have?
Still 2.
No,
Two
we have
equivalent equations.
well, it looks like two, but let's look carefully how they look like. What is the first
They're
equation?
equivalent. They give the same result, a equal to b.
So this is 5, this is 3a is equal to 3b, right? This is what the first equation really is. The second equation, if we look again, we get minus 3a. This is equal to minus 3b. So we take 5 outside. So it looks like we have two unknowns, but in principle, we have only one equation. So
if a equals to b means that every vector x cc with a value cc is okay. So
Yes.
1, 1, 2, 2, 3, 3, every vector.
yes, that's true.
When lambda equal to 2.
Yes, of course.
That's correct. Whenever lambda is equal to 2, any vector that is in the line y is equal to x. We are used from high school. We know how the graph of y to x is equal. It looks like, so 1, 1, 2, 2, minus 1, minus 1, minus 0.5, minus 0.5. They are all values which satisfy this condition. So then we can erase this one, and it looks like from these equations that we have here, for lambda equal to 2, the eigenvector, let's consider this x1, which is a vector, or let's write this one v1, because x denotes the polynomial, which is still on the board. So here we have v1, and this is equal to 1, 1. But we put a comma, we can say also minus 1, minus 1, and we can also write this one down. Now, it is very essential, often, to write this one magnitude 1, which would be, we can divide by 1 over square root of 2, 1, 1. So, representing these vectors as length 1, it is very important. Now, you remember how we got this. Allow me to take this away, because we know that the lambda will be equal to 8. So this was one of the lambdas, which apparently we found two values. Now let's consider the other case where lambda is equal to 8. If lambda is equal to 8, we obtain another relationship, which is 5 minus 3, 5.
Times AB equal to 8 times AB.
That's correct. This is going to be equal to 8 times AB.
Isn't it the same case? We get A equal to B?
A equal to minus b in this
Do
case.
you expect this, or do you expect a different value?
Well, either A equal B or either A equal to minus B.
Let's see. So
A
let's
equal to minus B.
the first
That's the
equation that
equation.
we can come up here is this. We have 5a minus 3b, 5a.
Equal to 8A.
This is equal to 8a. Yes. Do we need to write the second equation?
No, they're equivalent.
Shall we
They're
write
the
the second
same.
equation? Yes.
And from the first equation, we get
We get
3A equal to minus 3B.
Well,
3A equal to minus 3B.
this is 3a. This is equal to minus 3b. So in
Or
principle,
E equal to minus B.
AB, or we can add that this new second vector v2, vector v2, this is equal to 1 minus 1, or minus 1, 1, they are the same, okay? Or 1 over square root of 2, 1 minus 1, okay? So it looks like for these, the two vectors which the matrix cannot rotate, these are the only ones. So it's 1 minus 1, 1, 1. Where are these vectors on the board?
Second or fourth quadrant.
Yes, they are there, but these vectors that are
They form the basis.
They from the basis.
they constitute the basis for this new basis where this matrix is diagonalized. Okay, so it looks like if we want to, where did we come from to this point? Apparently, we mentioned this before. We said that it looks like if we want to diagonalize this matrix, this means that we have to change the basis from the standard basis, which is x and y, where the standard basis is composed of 1, 0, and 0, 1. We need to move to a new basis where the basis vectors, they look like 1, 1, minus 1, 1. And these, we found out before starting by this polynomial and represented this polynomial in this very elegant way, which has a lot of application in many different areas of science. And yeah, I can say 1,000 words about this one, but this is not relevant for you right now. But I can provide books of how essential representing very complex equations using the notation which is written at the edge, the second equation on the top of the board. It is very essential. Now, representing very complex equations or a series of equations, not only one, but you can denote thousands of these equations by using not only the matrix and the vector notation, but there is a little more developed concept, which is the tensor notation. And the tensor notation, what you can do is that with a single line of equation, you can write down up to 200 or 300 equations, because there might be combinations of which can be around. A good example of this one is, for example, let's say that the equations, the Einstein's equations of gravity. So what he has in there, he has x, y, z, including also the time in those, and he's taking respective derivatives of all of these quantities. So we have like 2 to the power 4 combinations come only from one derivative, and so on. So we can write them down, and you'll see that in a single line, we can represent hundreds of equations. But now, I just mentioned this one as a possible example, but there are many more like these, where we don't simply use a matrix, but we can also include something which is a generalization, which will be called tensors. Okay, so as we've said before, the most essential part of linear algebra is just diagonalization. We ended up into diagonalizing it, and we really notice. That's why we kept this equation here, because we wanted to make it clear that that these values, which apparently they come up in a unique way, because these are the values for which this equation will be satisfied. And another term that we can use here, which is equivalent to a lot of statements that are on the board, is the following: is that for this matrix, which has the off-diagonal terms different from 0, which are the -3 and -3, these are called the coupling terms. So it is coupling the x and y. Okay, But the moment that the off-diagonal terms are 0, we can say that the x and y, they are decoupled, okay? Or the x and y, they're projected onto completely different coordinate system, which are orthogonal, okay? So, do you have any question for what we have discussed so far?
No, I don't.
You don't. Okay, thanks. Now, we started from this example, but in essence, what we did in this part, we have also introduced the essence of chapter 8 of our textbook, which is finding the eigenvalues and eigenvectors. Okay. Now, these eigenvalues and eigenvectors, we know English very well. Some of you might know a little bit of German or a lot of German. And this eigen, this looks like it's in mathematics, which comes from the German school. And this means that these values and these vectors, they are spatial or inherent or associated quantities to a matrix. Particularly vera de Tiache, vera de matrices. Okay. So these eigenvalues and eigenvectors, they are, I think, they are very important ones. We need these eigenvectors because once we find the eigenvectors, we can find the basis. A week ago, or a couple of weeks ago, we discussed that, we said that, when we said that we're just stepping in the most exciting part of linear algebra, we said that we are going to do change of basis a lot. That's fine. But the bigger question is this: which basis is the best? Can a basis be the best possible one to work for a specific problem? Or can a new basis, which basis is the best to represent a complex equation like this? It's not that complex, but we can make it simpler. Which is the basis which can help us to simplify an expression like this, which makes it as simple as an expression like this, or this one, of which it is much simpler for us to figure out that in this case, this was an ellipse, because our eyes can draw this one easier than that one. So we wanted to change the basis, and what we are going to start from now on is that the best basis that we can use, that we can pick up, is always the basis which is composed of the eigenvectors. So depending on the problem, depending on the linear transformation, depending on what the matrix A is given in the standard basis, so let's not forget, this one is the standard basis. This one, the matrix A, this one, it will be represented in the new basis as a matrix D. And with matrix D, we denote a diagonalized matrix, because we like to have the diagonalization for many different applications, of which, for example, the dimension reduction is very essential. And this dimension reduction, we can use singular value decomposition to do a lot of data processing or data analysis and many more. Now, what we have on the board is just an example of how we solve the problem, but we have also the fundamental explanations of what eigenvalues and what eigenvectors do. And this is also very important information, which reports to us that we are going to work with vectors, or the vectors that we care a lot. They are not rotated by the matrix, but we just are modified by a constant value, which in this case is the lambda. Okay, do you have any more questions?
Professor,
Yes.
for the angle of rotation, is given by the exercise, or are we going to find it? In this case was 45 degrees.
Yes. Oh, yeah. So this is a good question. I thought you were asking in general. So in this case, it was 45 degrees. Assume that you did not know this. You can find the angle of rotation by doing what? By assume that we did not do this part. Then how would we come up to this problem here? We would have this matrix A, okay, and then we would do just this part, which is on this part of the board. We would find eigenvalues, we would find eigenvectors, and once we find eigenvectors, we would know the basis. Once we know this new basis, we know that 1, 0, and 0, 1, we can project, or this can come up into this new basis by rotating by 45 degrees. So if I give you another matrix, which is not 5 minus 3 minus 3, 5, but a completely different one, you can find yourself what will be the rotation. Okay? You can simply find what is the matrix. How can you do it? Because you know that this basis here is the matrix which is going to pass from the standard basis to the new basis. Okay? So your question was, how can you find the pi over 4? I'm saying that if we give any other matrix which is random, which is square matrix, you find eigenvectors, you write them down, and then you have to figure out what is the angle difference between this basis and this new one. Okay?
Okay.
Was I clear?
Yes.
Okay. Any other question? Okay. If you have no more questions, we can stop for today. I want to thank you for your attention.